introduce Chenrui. Chenrui has received his master's degree from Tongji University, Shanghai in 2012. He began his career as a hardware design engineer in Teradyne, Shanghai. In the first 5 years, he supported some famous customers like TI, BOSCH, STM, as an ATE Loadboard hardware engineer. In the last 5 years, focused on signal and power integrity simulation, and has provided hardware solutions for many kinds of chips successfully. So, Mr. Chenrui, please proceed with your presentation. Thank you.
Okay. Good morning and good evening, everyone. It's a pleasure here to do this presentation. And my topic here is the air over stub for 15.6 Gbps Serdes and mmWave. So this is the context of my presentation. First, I will give you an introduction to the background of my topic. And the second part, we will see what is the wear stop loss. And in the third part, we will introduce the two processes of the manufacturing of the PCB and explain the importance of their sequencing in the manufacturing. And then we will show some study results of and check what is the air over stub impact on the Serdes and on the mmWave. So for the Serdes, we will focus on the air over stub, the structure itself, and on the mmWave, we will focus on the backstream size, its impact. So, and at last, we will do a summary of my presentation. Okay, so firstly, I will give you some introduction to the topic. In nowadays, high frequency applications keep challenging on the PCB manufacturing capability and the simulation accuracy. And wear is a very common structure on the PCB. And the wear stop loss will do affect on the high frequency signal qualities for any usage. And air over stub is a kind of a manufacturing process to improve the performance of wear. So this presentation will analyze the impact of the wear stop loss to the 15.6 BPS Serdes and the mmWave signals. And then introduce the high frequency signal integrity improvement by the air over stub. This is a structure of the wear. Okay, so let's see what is the wear stub loss. So there are actually two kinds of loss. The first is the reflection, and then the second is the radiation. So on the left picture, we can see this is actually a time domain reflection, the TTR curve of some signal paths on the PCB. So we can see there's many discontinuous areas on the signal paths, and each discontinuity part will do affect and bring the energy loss to the signal. And of course, will be an obvious discontinuity point on the signal paths. So each point will bring the reflection, and then bring the signal loss. And on the right, this is a electric field curve from our simulation software. So we can see on the signal path, this is one signal path. We can see there are many places have the radiation on the trace, on the vias, and on the via stub. After introduction of the via loss, we were going to discuss the two process of the PCB manufacturing. So one is the explosive filling and one is the backfill. So in our PCB design for some critical signals, we will request to fill the planted through-hole vias with non-conductive materials, something like the explosive, and then do the backfill to minimize the stub length. So here is a very common plated through-hole via process in PCB manufacturing. So after PCB layers lamination, we will do the via drill and via planting, and then do the via fill holes, and finally do the via backfill. So this two-part sequence is very important to the signal quality. So we will discuss the importance of the two sequences. On the left one, we do the backfill first, then do the filling. So we can see when we have a planted through hole fill, and then do the backfill, and then do the fill. So after finish it, we will have a back drilled fill, but filled with the exposure on the full pass of the vills. But if we do the filling first, we will have a very different finished vill hole. The exposure will exist on the single pass, and in the back drilled area, we will have the air over the start. So this will bring very different result to our signal pass. From these two slides, we knew the two producer of the vill processing, and these two different finished structure caused by the different sequences. Then we will see the different performance caused by these two structures. Let's first focus on the Serdes signals first. So we will analyze the impact on the Serdes signal first. And our study object is a very simple differential pair loopback layout in the PCB. It's on the inner layer of the PCB. So this is the layout from the EDA tool. So if we on the top there are two pictures. This is a E field at the 15.6 gigahertz, and this is the E field of the dielectric overstop. So we can see the field is leaking to the air in this stub area. But for the air overstop, you can see there's the energy is nearly not leaking into the air over the stubs. So this is the study result of the electric field, and then we will discuss the S parameter from the simulation. So let's focus on the blue line. This is the insertion loss of the two kind of structure. So we can see a big difference on the high frequency, especially on the 15.6 gigahertz. So we can see the dielectric overstop will bring minus 35 dB on the 15.6 gigahertz. But for the air overstop, we will have only about minus 20 dB. So the difference between these two structures will be about 15 dB, I think. So this is a much big difference because caused by the stub radiation at the high frequency. And then we will discuss the air diagram from these two structure. And the left is also the dielectric overstop, and on the right is the air overstop. So we can see clearly, the right one is more clearly, right? Sorry for the small test, but on the left, the air height of this structure is about 480 milliwatt. For the air overstub, the air head is about 533. So air head is about 10% big to the dielectric overstub, thanks to the low loss we see in the insertion loss. Okay, next we will discuss the impact of the bacterial size. First, we will see the electrical field at the 15 gigahertz. And we can see also in this area, it will be the energy leakage into the air or to the dielectric materials. And for the air overstub, there's also nearly no leakage into the air. And what we wanted to discuss is here. So we can see a cylinder here. So we will change the diameter of the cylinder here to check the result and check what is the impact on the signal quality. Okay, we will shoot. First of all, we will show two kinds of results. One is the TDR, time domain reflection, and one is the insertion loss of the different bacterial size. So we can see the small bacterial size is about 1 micrometer, and the biggest bacterial size is about 0.6 millimeter. So we can see maybe at the 14 gigahertz, the difference is not too big. It's minus 0.812, and versus is minus 1.06. But at the higher frequency, at the 16 gigahertz, we can see the difference is very obvious. So for the smaller bacterial size, it is about minus 15 dB, and for the biggest bacterial size, it is about 6.69 dB. So this is about one-time improvement for the higher frequency. And on the left, this is a TDR curve. So we can see the bigger bacterial size will reduce the capacity of the stub. So the impedance of this stub will go higher of the impedance, and which is more close to our target impedance, 15 ohm. And this result is talking about the return loss. To remind you, this is the red line in the smallest bacterial size, and the purple one is the biggest bacterial size. So the return loss is improved by the big bacterial diameter. It's reduced from the minus 11 to the minus 17 almost at the 43.5 gigahertz. So this is a very big improvement for the high frequency signals. Okay, at last, I will give you a summary of my presentation and the study. First, we will talk about the manufacturing. So for the manufacturing, from the perspective of the signal integrity SI performance, we prefer the spice over stub to be filled with air rather than the dielectric. For the high frequency PCB application, bacterial process prefers filling first and the bacterial last. And this should be addressed on the on the fab nodes. And from the perspective of a simulation, for the high frequency simulation, the LO step needed to be taken into consideration when we do the design. And the big backfield diameter might improve the high frequency signal integrity for the case of LO step. Okay, and thank you. This is all I want to share in this presentation.
Okay, thank you so much for your wonderful speech. So let's check the questions. Okay, the question is, how to define the particular wire process with fab weather?
Okay, in our PCB design, we will always give our final document file to the fab vendor. And there's always be a fab note page and to define some special request to PCB vendor. So we should address this via process on that page to keep aligned with the fab vendor. We're on the same page for the different sequences of the via processing.
Okay. And another one is, does the backdraw vice has a residual stub? What is the length?
Okay. Yes, of course, the backdraw will always have a residual stub. And for current technique, I think the stub lasts about 12 mils in general. It's according to the fab vendor capabilities.
Okay. So the last one, we checked the last one. What is the wire size discussed in mmWave case?
I think you are pointing to the wire diameter of this wire. This is a 0.4 millimeter diameter of this wire drilling.
Okay, thank you so much for Mr. Chen. Thank you for your wonderful sharing.
Okay, thank you, Rui.
I'd like to thank the sponsors before we go into the sponsor hangout with Smiths. But first, JDT Technology, Automation and Intelligent Integrated Solutions Supplier. And Smiths Interconnect, your global partner for innovative semiconductor test solutions. Teradyne, enabling the next generation of technology through advanced test solutions. So I thank all of them for sponsoring, which have made this these presentations open to everyone free of charge. And I want to thank everybody for joining us today and look forward to seeing you tomorrow and on Friday. So thank you. Have a good rest of your day.